Okay, next is a reminder about the cross product and the triple product. So I'm not going to extend on that. We've already worked on that together at the very beginning of the year, and you worked on that maybe in other topics and maybe last year. So I assume you all know how to make a cross product. This is what we're going to need. Um, all right, and there's just one piece here about the that is directly linked to the orthonormal basis. Uh, it's the part about the orientation here. So if you have two orthonormal bases, B and B prime, and so we already know that the change of basis matrix is orthogonal, and so it has the determinant of plus and minus one or minus one. And so we're going to say that those two bases define the same orientation if the determinant of the change of basis matrix is equal to plus one. Okay, and so you are reminded also with what we are what we call the positive orientation, and how you can define that in the usual space you are living in. So you have this right hand rule. Okay, so I let you read that again calmly later on the triple product. And what I really will need you to know how to do is that cross product, because we're going to use that later on, and you have a few reminders. And well, what's important is that when you are computing the cross product, given in R3, okay, so with some x and some y. This is how you compute it, and what you are creating is going to be a third vector that is orthogonal to those two ones. Okay, the result of the cross product between x and y is something that is orthogonal to x and orthogonal to y. Okay, and it's going to be in the direct okay, x y, x cross y make a direct basis of E. Okay, so this, I assume that you know how to work with that. Otherwise, please revise this part. Okay, let's go to what really we want to do in that chapter, the orthogonal transformations. Another word for that is linear isometries. Okay, let's begin with the definition. So we are in our nice Euclidean space with this so finite dimensional linear space with a nice inner product, and so it has a norm that is associated to this inner product. Let's consider F an endomorphism of E. It's called a linear isometry, or a synonym will be an orthogonal endomorphism if if and only if one of the following conditions is satisfied. Well, it preserves the norm in the sense that if you take any element x, um, any element, sorry, any element x in E, its norm is going to be equal to the norm of its image f of x. Okay, so it preserves the norm. That's the definition of isometry, same length, right? Or another way to say that is that it preserves the inner product, meaning for any xy, the scalar product of xy is equal to the scalar product of their images, f of x and f of y. Okay, and the set of all orthogonal transformations of N of E is called the orthogonal group of E, and it's denoted O of E. Okay, so we have the orthogonal group of a linear space. Earlier we talked about the orthogonal group of Rn, which were the set of all orthogonal matrices. Okay, here we are not, maybe not in Rn, we are talking about any Euclidean space, well, it's of dimension n, but you know that we will be able to build an isomorphism. Well, we know how to build an isomorphism between a space of dimension n and Rn, and so it's going to be actually very similar. Okay, Okay, next. So let's have a look at this proposition. If F is an orthogonal transformation of E, then F is an automorphism. In other words, F is bijective. Let's prove that. Okay, so let's prove this first part. So we assume F belongs to, sorry about this, we assume F belongs to the set of all orthogonal, well, the orthogonal group of E. What does it mean? It means that for any x, y in E, I'm just reinterpreting this hypothesis. Scalar product x and y is equal to the scalar product f of x with f of y. Okay, all right, that's the definition. Let's see. Let's consider a basis, right? We know we've got this orthonormal basis of E. Well, we know it exists because it's a finite dimensional space with a nicely defined inner product. Okay, so it has n elements. And let's consider f of E1, f of En, right? The family that is made out of the images by f of these basis elements. What do we have? Let's have a look at f of Ei, scalar product with f of Ej. By definition of linear isometry, that is going to be equal to the inner product between Ei and Ej, which is according to, well, because B is an orthonormal basis, this is going to be equal to delta ij, you know, that canonical value equals to 0 if I different from j and equals to 1 if ever they are the same ones. So what does that mean? The vectors fei, fej are going to be equal to 0, so in other words orthogonal, right? If I am not considering the same ij, and if I'm considering the same one, it means that the norm of fei is equal to 1. Okay, so actually f of ei, e1, f of en make an orthonormal basis of E. Okay, and I let you think about why this implies that f is invertible. Okay, so why well, that's a property we saw in the previous chapters, but I remind you why makes infinite dimensions, what makes a map an isomorphism. You know that in that case it's going to be equivalent only in finite dimension. I insist to the fact that it's an injection or a surjection or a bijection. They're all equivalent in finite dimensions because you have that rank nullity theorem. So if the image of a basis is a basis, it means that your map has full rank. Its image, the dimension of its image, is the dimension of the space, okay? Because it makes linearly independent vectors, right? So that's it. It's in the image of a basis is a basis, so it's invertible. All right, so that was the first point. Second point, if f is an orthogonal transformation, then its inverse, we know now that it exists, is also an orthogonal transformation. So start by writing again the definition. F of x, f of y is equal to x, y. Okay, now put capital X is equal to f of x, capital Y is equal to f of y. You get that capital X is f minus 1 of capital X, sorry, capital X is, let me erase that, f of x, so small x, right, so capital X is f of x, some small x is equal to f minus 1 of capital X. Okay, so and small y is equal to f minus 1 of capital Y. So according to that, I can rewrite that equality as xy is equal to f minus 1 x f minus 1 y. Okay, hence it satisfies also the property of items in the orthogonal group. It's also an isometry. Okay, it preserves the scalar product. Okay, next one. Well, this is just that if you have two orthogonal transformations, then their composition is also an orthogonal transformation. Maybe I'll let you play with those kind of writings to alone. Okay, so it's really not complicated. Try to do it by yourselves. Right? So pause to that. Next, okay, so that theorem, given a linear subspace F included in E such that F is invariant by small f, that belongs to the orthogonal group, then the orthogonal of F is invariant by F. Okay, that makes a lot of play on words. So, let's cut that into some small pieces. Capital F is invariant by the small f in O of E. So what do we have? First of all, f belongs to O of E. It means that you know that for all x and y, we get x, y is equal to f of x, f of y. So that should be sort of a reflex for you when we say, okay, we've got f that belongs to O of E. Write the definition. Okay, capital F is invariant by small f. What does it mean? It means that for all x's that belong to capital F, f of x, the small f, belongs also to that space. That's what it means to be invariant. Then what we want to show is that f orthogonal is invariant by f. What we want to show is for all x that belong to f orthogonal, do we have that f of x also belongs to f orthogonal? So that's a question we want to answer. Okay, so maybe I will change my notations. Let's take some y. Okay, all right. So very simply, let's write that y belongs to f orthogonal and x belongs to f. What does it mean? It means that xy is equal to 0. Okay, but as f is a linear isometry, it means that the first scalar product xy was also equal to f of x, f of y. Okay, so and it's equal to 0, and we want to show that f of y sorry, we want to show that yeah, f of y also belongs to f orthogonal. So do we have that for all z that belongs to f, f of y scalar product with z is equal to 0. Okay, so as we know, as it is we've already shown that f is a bijection. F minus 1 exists, so there exists x such that x belongs to f with f of x is equal to z, because f, the big one, is invariant by f. And so I've got that f of y, f of x is equal, well, what I had, if I'm computing f of y z, that's equal to f of y f of x, and that's going to be equal to 0. from what we got earlier, right? So y belongs to the orthogonal